Good day everyone. In Chapter 2, they demonstrated how a linear programming model is formulated and how a solution can be derived from a graph of the model. In this chapter, we will show how linear programming problems can be solved using several personal computer software packages. We will also describe how to use a computer solution result to experiment with the linear programming model to see what effect parameter changes have on the optimal solution, referred to as sensitivity analysis. When linear programming was first developed in the 1940s, virtually the only way to solve a problem was by using a lengthy manual mathematical solution procedure called the simplex method. Simplex method is a procedure involving a set of mathematical steps to solve linear programming problems. As a result of the easy and low-cost availability of personal computers and linear programming software, the simplex method has become less of a focus in the teaching of linear programming. However, knowledge of the simplex method is useful in gaining an overall in-depth understanding of linear programming for those who are interested in this degree of understanding. Excel can be used to solve linear programming problems, although the data input requirements can be more time-consuming and tedious than with a software package like QM for Windows that is specifically designed for the purpose. However, this is also an advantage of spreadsheets in that it enables the problem to be set up in the attractive format for reporting and presentation purposes. In addition, once a spreadsheet is set up for one problem, it can often be used as template for others. QM for Windows provides mathematical analysis for operation management, quantitative methods, or management science. It features calculation methods for PART or CPM, linear programming, decision analysis, transportation problems, statistical function, game theory, goal programming, and etc. The PART or CPM is used to assist the project manager in scheduling the activities. Example, when should each activity start? In PART or program evaluation and review technique is used to assist in project scheduling, similar to CPM. This program can be helpful for students who are following management science texts such as Introduction Management Science by Taylor, Quantitative Analysis for Management by Render, as well as the Operation Management books. This time, we will show you how to use QM for Windows for our linear programming problem. From YouTube, credits to Gary DeBoch.
Changes in objective function coefficients. Objective coefficients tells you the coefficients that are associated with each decision variable in the objective function. The range of optimality for each coefficient provides the range of values over which the current solution will remain optimal. Managers should focus on those objective coefficients that have a narrow range of optimality and coefficients near the endpoints of the range. Here is the first important observation about changing the coefficients of the objective function. This does not affect the feasible region. For this reason, the optimum point that you found during the original solution of the problem will remain a feasible corner point. The worst that can happen is that the original optimum corner point will no longer be optimum after the objective function is changed. In that case, you can probably restart the solution at the original optimum corner point and continue iterating until you reach the new optimum. The simple ranging analysis will tell you whether you have to do this or not. As you can see on the screen, we will show to you an example of what will happen when changing a coefficient in the objective function when it tilts. The example A shows original objective function. B shows a tilt which does not change the optimum basis, and C shows a tilt which changes the optimum basis. If you are investigating a change to an objective function coefficient, just compare the change to the ranging table. If the change is more than allowed, then you have no option but to resolve the problem to find a new optimum counterpoint. Most commercial solvers allow you to restart any basis. If you have any previous saved to optimum basis, then restart there since the new optimum is likely to be only a few pivots away, or you can restart the model from scratch in the worst case. But what if the proposed change to the objective function coefficient is within the allowable range? Then, how do you determine the new values of z and the variables? This is straightforward. The new optimum variable values will be the same as in the original solution, because the constraints are not in change by modification to the objective function, and we are the same basis, so we will be using the same place in space. You can calculate the new value of the objective function easily. Just substitute the old values of the variables into the new objective function. Alternatively, since only one objective function coefficient at a time is changed, you can calculate the change in the objective function value by calculating the difference due to the change coefficient. Now we are going to use the Acme Bicycle Company problem for the example presented in the next slide. For an example, is the Acme Bicycle Company solution sensitive if the objective function coefficient is x1 is changed from 15 to 25? As you can see from the table, the allowable increase for the objective function coefficient for x1 is infinity, so the basis will remain the same. The optimum solution will still be x1, x2 equals to 2 and 2, but the new z will be given by 25x1 plus 10x2 equals to 22 plus 10 times 2 equals 70. You could also calculate the new z by looking only at the change coefficient. What about changing the objective function coefficient of x2 from 10 to 25? As you can see from the tables, this is a change of 15 units, which is greater than the allowable increase of 5. This means that the basis will change. So the only way to find out what the variable values and the z will be at the new optimum is to restart the solution and continue iterating until you reach the new optimum point.
Good day everyone, my name is Melanie Ardrus. I'm going to explain to you the objective function coefficient ranges with the computer solution. When we provided the Excel spreadsheet solution for the Beaver Creek Pottery Company, Excel will also generate a sensitivity report that provides the sensitivity ranges for the objective function coefficient. When you click on Solve in the Solver parameter window, you will momentarily go to a Solver results screen, which provides you an opportunity to select different reports before proceeding to the solution. At the next slide, that will be the sensitivity report for the Beaver Creek Pottery Company. In this chart, you can see that there are columns that shows the allowable increase and allowable decrease. So before that, we are going to focus on adjustable or variable sale at the first table. The first information can we get from this table is that we see the final value. This gives us all the ultimate solution to our problem. The complete range for the x1 coefficient is equal to 25 lesser than C1 greater than 66.67. Also, the sensitivity range for the x2 coefficient is equal to 30 lesser than C2 greater than 80. The objective coefficient, the 40 and the 50, tell us the coefficient that are associated with the decision variable in the objective function. So, in this problem, the coefficient was the profit per unit for bowls produced and objective coefficient was the profit per unit of mugs produced. The profit for the bowl can vary between 25 and 66.67. Also, in the profit of mug can be vary between 30 and 80. In adjustable or variable cell, we can actually look at how our optimal solution. Optimal solution is the objective function reaches its maximum and minimum. How our optimal solution or objective function value changes with the objective coefficient value. Notice that sensitivity ranges for the objective function coefficient are not provided as an upper or lower limit, but instead shows us the allowable increase and allowable decrease. So for the x1 40 coefficient for bowls, the allowable increase of 26.67 results in upper limit of 66.67, wherein the allowable decrease of 15 result in a lower limit of 25. Paano nakuha ang allowable increase na 26.67 and allowable decrease na 15? So the solution is the 66.67 or our upper limit is subtract natin siya sa ating objective coefficient na 40. So the equal is 26.67. Ganun din sa allowable decrease. Ang 25 or our lower limit is subtract natin siya sa ating objective coefficient na 40. So the equal is 15. Same thing in the x2 50 coefficient for mugs. The allowable increase of 30 results in an upper limit of 80 and the allowable decrease of 20 results in low limit of 30. So ganun din, para makuha ang value ng allowable increase and decrease, all we have to do is to subtract the upper limit into the objective coefficient. The equal will be the allowable increase, and to subtract the objective coefficient into our lower limit, and the equal would be the allowable decrease. So for the solution in QM for Windows, the same thing, we're going to focus on adjustable or variable cell. Let's understand that this information that you see in Excel, this is actually the same information, just slightly different format. Basically shows something called the range of optimality. For each objective coefficient, the 40 and 50, we are given range of optimality. The range of optimality is just a range of values. It defines in the x1 coefficient that 40 plus the allowable increase 26.67 is equal to 66.67 for the upper limit or upper bound range of optimality, and 40 minus 25 will be the equal to 15 for the lower limit or lower bound range of optimality. Same thing on the x2 coefficient. It defines in the x2 coefficient that is 50 plus the allowable increase 30 is equal to 80 for the upper limit or upper bound range of optimality, and 50 minus 20 will be equal to 30 for the lower limit or lower bound range of optimality. The range of optimality for each coefficient provides the range of values over which the current solution will remain optimal.